control session. My name is Sterling Anderson. I'm coming from the MIT Robotic Mobility Group. I'll be chairing this session as well as presenting the first paper. Our second speaker, Lamri Nahawa, has had some trouble catching his flight in Paris and will not be presenting his paper, Backstepping-Based Approach for Combined Longitudinal Lateral Vehicle Control. But we encourage those of you who came just for that paper to stay for the other two, because they'll be good. So, and the third speaker will be Jean-Philippe Laufenberger. He's an associate professor in MIPS, and I'll give him a more proper introduction at the conclusion of my talk. So we'll just start right off with this. So as I mentioned, I'm coming from the Robotic Mobility Group. I want to give attribution to some of my colleagues. So Cecile Karumanchi and Carl Yanyema were my collaborators on this work. And we did a lot of the experimental work in collaboration with a company called Quantum Signal LLC in Michigan. And I'll talk to you a little bit about the components of that they were involved in. So to begin with, this is a problem that needs little introduction, and we've all been discussing it sort of all day long. So I won't belabor the point that human error is a big deal when it comes to operating machinery. In various domains, we see that in spite of advances in the design of machines and even of safety systems, as long as humans control those, we will be subject to human error in some way, right? Our work is specifically focused on how do we allow the human to work in conjunction with the autonomous system such that humans' inputs, which in many cases are based on superior perception, judgment, and reasoning, are honored where possible and overrided where necessary to avoid collisions or loss of stability. So that's what we're focusing on. There was a study done of collisions in the UK and the United States a few years ago in which human error was cited as a sole factor in 60% of collisions, a contributing factor in 95%. So that's the statistic we're up against when it comes to overcoming sort of human error. So I think a lot of people would ask, well, you know, if human error is so detrimental, why not cut the human completely out of the loop? Why not an autonomous system? And in fact, many autonomous systems have been proposed today that are very good, but for a number of reasons, we don't believe that humans will be ready for full automation for many years to come. A few of those reasons include, number one, our superior judgment and reasoning. Right, particularly in military applications right now, the law in the books is that only a human can target and or fire upon an enemy combatant. For example, you don't want a bunch of Terminator-type figures running around shooting at combatants. There are high automation costs in many industries. And finally, there are significant socioeconomic pressures. So in the United States, for example, were we to try to automate the transportation of goods, we would have significant conflicts with, for example, truckers' unions and others who would be looking at being out of a job were humans cut completely out of the loop. So how do we do this then? Right now, the proposals sort of span two sort of distinct sectors, right? We have full automation on one end of that spectrum, and we have ADAS or driver assistance systems on the other. Typically, as a general rule, full automation considers both strategic and tactical goals. Typically, there's a planning component in a tiered subsystem architecture with a low-level controller. Operator assistance, on the other hand, tends to be more tactical. It tends to be less predictive in nature and more monitoring vehicle side slip in the case of stability controllers or longitudinal side slip for analog braking systems and traction controllers and others. Where we are focused is somewhere between these. We've developed a semi-autonomous navigation system that aims to integrate both some of the strategic elements of current autonomous systems with regards to a capability of planning better routes for the vehicle if the human's inferred route appears unsafe, but also in managing a lot of the low-level control aspects that will ensure that the vehicle avoids collisions and losses of stability. So the basic approach to this, as I've outlined here, We assess the threat of a situation once we've designed a set of constraints, and we modulate or allocate control between human and machine in a fluid fashion to ensure that the obstacles are avoided, collisions are avoided. So some key questions that we had to ask, or that we have to answer when it comes to modulating control like this is, when do you assist the human, how, or in what form, and how much, right? And all of this has some pretty significant implications when it comes to sort of the human performance and the human acceptance of that assistance. Now, there are some synergies we think we can exploit between humans and automation. As I mentioned, humans tend to be a little better at perception, judgment, and reasoning. On the other hand, automation tends to be a little better at repetitive tasks, at precise low-level control. A lot of this was written about by our colleague Tom Sheridan years ago, and continues true in our research, and I'll talk a little bit about how it's borne out in some of our experiments. So the key insight that's driven our approach, before I get into sort of why we're doing this, I'll use the phrase constraint-based a lot, and the reason for that is that's sort of the principal differentiator of our work, is we're focused explicitly on the design and selective enforcement of constraints rather than reference paths, which is sort of, I think, makes this work a little bit different, and in many ways, I think, a little better suited for this type of semi-autonomy. And here's the reason. Humans tend to operate not along a specific path, but instead within a field of safe travel. For example, when you're driving a vehicle along the road, you typically see the lane that you want to remain within and constrain yourself to remain within it, rather than, except for maybe in a few sort of obsessive-compulsive disorder cases, you will control the vehicle only insofar as it keeps you within the lane. It's not super significant to you whether you're following a specific line on that lane. And if we plan a reference path and control along it, a modular, sort of a fluid semi-autonomy approach can be over-restrictive at worst and arbitrary to the human at best. It can be difficult to determine, for example, if the human wanders 2 inches or a foot away from the line, is that when we start to apply control authority to get him back? Do we wait until he crosses the edge off of the lane into another? And so we focus on, how do you design the constraints that bound the region of the environment that the human should remain within? And then once you've designed those constraints, how do you apply them in such a way that you don't over-restrict the human from what he or she wants to do, but you also can ensure that any collisions are avoided? So the requirements then of this are, first we have to design the constraints, then we have to assess the threat of the scenario, and by threat I mean the nearness to instability of a predicted optimal vehicle path that satisfies those constraints. And then finally we have to design a semi-autonomous intervention mechanism, or a means by which the autonomous controller can intervene when necessary to ensure that those constraints are satisfied. So what you see here, I've just sort of illustrated, overlaid on a typical view of an environment from a human's perspective, what 3 different path homotopes, and I'll define that in a second, but 3 different sort of corridors or channels or fields of safe travel that you would typically identify as a first high-level identification of the environment that you want to travel through. There's the green, the yellow, and the red, sort of correlated with, typically you would likely see this green region as the safer one, in that it requires less immediate control action to remain within. But we'll get a little bit more into that. First, I'd like to describe the system architecture. What we've done is we use look-ahead sensing, which includes LiDAR and cameras for a terrain and obstacle identification. From that, we pass a map of configuration space or free space to a constraint planner. That constraint planner identifies the feasible regions of the environment and designs constraints on the position of the vehicle, on its slip and other stability states, as well as on its control inputs, to ensure that it remains within that. And that's here is identified by this red sort of bounding. You'll notice that prior to that constraint planning step, going right or left would have been deemed sort of a wash. But we've got to decide in that a set of constraints cannot include any of these collision states, The constraint planner chooses which is safer. And then we have an optimal trajectory generator and controller that's being done with model predictive control with a model of the vehicle. So that plans an optimal vehicle trajectory through those constraint sets that satisfies them and calculates an optimal sequence of control inputs. Now, as those of you familiar with model predictive control will already know, a model predictive controller gives you, along with the sequence of optimal control inputs, also a sequence of optimal vehicle states, right? Each one of which needs to satisfy a set of stability critical limits or constraints as well. For example, the slip on the tires typically the tire friction force typically saturates around 6 to 7 degrees of slip on a passenger vehicle. Therefore, if you monitor the state, each of these predicted states, if any of those approaches that limit, the edges of the stability envelope, that implies a high risk, or it implies that even an optimal trajectory is getting near to the limits of the vehicle stability, and there is some need for intervention to avoid losing control. Finally, a threat assessor does exactly what I just described. It looks at the predicted states. It assesses how close we are to instability, and in accordance with that nearness to instability, it makes a decision as to how to allocate control between the human and the controller to ensure that we avoid collisions. So let me just describe a little bit what the constraint planning objective is then. As I mentioned, we identify regions in the environment that are sort of inevitable collision states. There are a number of ways of doing that. Others have presented some very rigorous methods. I just spoke with one in the poster session. Any of those can be used. What we're focused on is how do you design constraints to bound those. Here you'll notice a simulation where I've overlaid the blue vehicle is with the controller in the loop. The gray is what it would have done given a zero driver steer input. And what it's doing is planning constraints around these objects in the environment or the collision states, and then using the model predictive controller as I've described in this semi-autonomous fashion to intervene where the intervention is shown in green here as a percentage in order to avoid these obstacles. But here, the challenge with designing constraints, and we're all used to designing paths, right? And a lot of path planning literature has been developed for a long time. But when it comes to designing constraints, it becomes a little bit more difficult to characterize, for example, what's the length of a constraint? What's the width or curvature or dynamic feasibility of a constraint? All of these terms and all of these metrics are well defined when it comes to path planning. They're not well defined when it comes to a set of constraints which can bound an infinite number of vehicle paths. So that was the challenge that we set out to address. And we wanted to figure out how exactly do you characterize the goodness of a set of possibly infinitely many homotopic paths that pass through an environment. So let me just describe this word homotopy before I go on. For those not familiar, a homotopic class is any set of paths with a particular, with the same starting and ending point that can be continuously deformed without crossing obstacles. So for example, in the common driving scenario, a homotopic class would be a lane. If you were out sort of in an unstructured terrain, a homotopic class would be any set of paths you can take that sort of takes a certain route through the trees. Now, one of the important considerations for us with regards to homotopic classes was that each path in a homotopic class has to traverse a specific capture set. When I talk about capture sets, what I mean are any of the set of states that exist within that homotopic class across which every path existing therein will cross. Okay, and one of the ways that we use that is here I'll just sort of identify a number of homotopic classes, right? Each of these colors represents a specific class about which constraints can be designed to bound the vehicle state. Well, if we use something called constrained Delaunay triangulation, we can essentially set up each of those capture sets as these sets of adjacent edges between triangles across which vehicle paths will cross. And as the vehicle, and if we use a number of metrics, which for the sake of time I won't get into, to describe how the state evolves from one capture set to the next, we can describe the dynamic, sort of bulk dynamic feasibility of a constraint set. And that, in essence, becomes our metric for goodness of a given constraint set. And as you'll notice, there are a number of constraint sets that could exist. You know, we could have taken any of these homotopic classes, but using some of these geometric constructs, which you can read more details about in the paper, we can design a chosen homotopic class. Now, some of you who will notice that this looks an awful lot like, when we use constrained Delaunay triangulation, some of these metrics look a lot like the Voronoi diagram. And the reason for that is quite simply that the Delaunay triangulation is the geometric dual of the Voronoi. So that gives you some indication of, in essence, the length of the sort of medial path that traverses a given homotopy. So I'll skip through that. So what I want to describe now is sort of how we enforce those constraints, what the mechanism is for semi-autonomous intervention that we've used to ensure that we can traverse this homotopy without colliding. So as I mentioned, low threat, those predicted states are far away from the bounds of vehicle stability. High threat, they're very close. What we do is just configure the controller to satisfy constraints while minimizing any of a number of vehicle states that indicate stability. It can be lateral acceleration. In our case, we use front wheel side slip. And we call threat the nearness instability, as I've mentioned. Here you'll see just a simulation showing what was happening, for example, in that vehicle simulation I was showing you earlier. The trace of the vehicle is here in blue. The red is the predicted trajectory of the vehicle, and the green are the constraint sets. You'll notice that as the predicted trajectory begins to bend, the predicted states become nearer to the limits of stability. And in accordance, our control authority is allocated here. When control authority allocation is 0, that means the human has full control, which is sort of as we'd like it to be. As a need for intervention arises and the human does nothing, that intervention increases just enough to ensure that the controller can turn the vehicle around and satisfy the constraints. So here you'll see again, blue vehicle shows with or semi-autonomous controller in the loop. Gray vehicle shows without it. Here I've used just a poorly tuned pure pursuit controller for my driver model. And that shows that, you know, obviously I tuned it poorly for a reason, just to demonstrate that same driver model, in fact, the same driver model is being used in both cases. Here on the left, it shows you how much control authority is being allocated to the controller in the blue case. I would note that for a lot of drivers, for example, when we had some drivers up at Ford test this for us, you don't notice intervention below about 60%. It just kind of feels like you're doing a great job, and you're not sure how much the controller is intervening, and that's sort of as we'd like it to be. So if we introduce a delay, I wanted to mention that here's the trace of the vehicle path. You'll note that, as I mentioned, we're only imposing constraints on the position of the vehicle. We're not imposing a reference path. But the interesting thing is here, the reference path for the driver model is the very center of this lane, this blue dashed line. Notice that when the controller is off, in the gray case, the driver in this yellow line sort of loses control and leaves the roadway. When the controller is on, not only does it stabilize and keep the vehicle within the lane, it enables the driver to keep it closest to whatever reference path he or she would like, which, as I mentioned, drivers don't typically choose reference paths, but if they had, or if they did, this is actually an enabler. Notice how the trace of the vehicle, the red line, actually stays very close to what the driver model in this case is trying to track. Another place where this works quite well and will sort of motivate the final set of experiments that I'll demonstrate to you is in teleoperation scenarios. In teleoperation, one of the big problems tends to be time delay, both in sensing and in control, right? There's a 200 millisecond to 500 millisecond delay between when control inputs are sent and received at the vehicle. That time delay tends to destabilize a lot of drivers. And here I've done the same scenario, but with time delay, and we get a very similar outcome. If we run this controller on the vehicle itself, and therefore not subject to that same time delay, it is again able to stabilize the vehicle while still allowing the human significant control when the human's inputs are safe. So here I'm just demonstrating the same controller as it would be performed through an arbitrary obstacle space. Here the constraint planner is planning via these Delaunay triangles. If we throw in an additional obstacle here, a sort of a naive path, planner would have chosen this sort of tortuous path, which is unachievable via model predictive control. If instead we integrate some of these the capture set or dynamic considerations, it in fact plans what turns out to be the better homotopy. So finally, I want to just show sort of how this has been implemented in an experiment on a teleoperated vehicle, and then we'll take a few minutes of questions. So the hardware that we're using is a semi-autonomous Kawasaki Mule, developed in collaboration with our partners, as I mentioned, at Quantum Signal in Michigan. The sensing is being done via Velodyne LiDAR, and we've got a video head up front for the teleoperator to view, a Navcom GPS microstrain IMU. And we've got a PC, as I mentioned, on board running the control code, and therefore not subject to latency or communication issues. Now, what we've done for some of our tests is we've given the operator, who's just sort of untrained guys, each of which has a driver's license but nothing more. We've asked them, okay, from a teleoperated sort of station, which is inside a barn from which they can't see the vehicle via line of sight, they have to rely on the monitor. We want you to navigate this vehicle from the start to the other end of an obstacle field. And we don't want you to hit any barrels, and we're going to throw the following sort of challenges at you. Number one, we're going to cut out the video occasionally. So you're going to be driving blind, which is something that would be quite common were, for example, the sensors of cameras obfuscated via, for example, sand or fog or otherwise. We've also asked them to perform a secondary task on a different computer, which is something that would be common in military applications. And we've also introduced communication delays of 500 to 2,000 milliseconds. And we've done over 400 user trials to date with very good results, and I'll describe those. But there are a couple of feedback mechanisms that we wanted to provide to the human. Number one is, and we're actually quite excited about this, and that is when we plan these constraints, right? We've already mentioned that humans tend to operate already with this sort of constraint frame of mind. When we plan these, we can actually help the human identify sort of the preferred homotopy. We can help them identify the lane. We call it the yellow brick road, right? That sort of would be best to follow for dynamic and safety considerations. And that is overlaid on their screen along with sort of an indicator of what the vehicle is doing. Here's another example of that. And we won't talk about this today, but we've also recently started testing sort of a reduced fidelity sensory feedback where they don't even get video. All they get is the yellow brick road being sent from the sensing computer, so we can sort of reduce bandwidth substantially. All they see is this, and they actually tend to perform quite well. They can sort of stay within the lane that we've outlined for them. So I'll skip through this very briefly, but we're also providing torque constraints or torque feedback to the human, and the way we're doing that is we're saying, okay, here's the optimal input. As I mentioned, as the vehicle approaches something and that optimal input becomes more and more urgent, in a sense, in order to avoid the obstacle, we increase the stiffness on deviation from the controller's optimal input. So what effectively ends up happening is the steering wheel begins to pull one way. Not that you allowing it to go that way is critical to the vehicle doing what it's going to do, because it's going to do that regardless, but instead with the objective of improving the operator's situational awareness, we sort of move the steering wheel towards where the vehicle is actually going, so that they know what's happening. Here's a video illustrating this approach. You'll notice that the cayenne lines are the constraint set. You'll see the corridor through there. The red is the predicted trajectory. Notice that in most cases, as the driver drove through that, we allowed them to change, we allowed those constraint sets to change as the driver pushed the vehicle to one side or another. But as we came close to, so here we're allowing it to change. As we came close to the bush here at the end, that was sort of deemed a critical constraint, and we didn't allow it. Sorry, it was right there. We didn't allow it didn't allow the driver to collide with that. This controller tends to improve sort of or reduce oscillation in the driver commands when there's delay. Here's with the controller. There was without. We also show a number of improvements in, for example, average velocity. Drivers tended to feel more comfortable with the controller in the loop because they didn't feel like they were going to hit things, and they drove a little faster. They used less of the steer in every scenario without our controller in the loop. The driver saturated the steering input at one point or another. With it, they didn't. Here's sort of a typical trace. I'll let you read through the paper to see more of this. It's a little difficult to see here. But bottom line, the constraint-based semi-autonomy improved collision avoidance by 60 to 70% in each of these trials. We attribute that final 30 to 40% margin to the significant blind spot we have with our current LiDAR setup, which we've since resolved, but it's definitely in the results you'll see in this paper. And then this is just sort of a summary of the results. Again, with no assistance, we had a success rate of 5%. With assistance, with no delay, it was, with no assistance and with delay, it was a 0% success rate. Increased to around 70% with assistance. Here's just a video of what's happening here. You notice the corridor is being sort of these constraints are bounding regions of the environment that we prefer the driver not to navigate within, and the intervention mechanism is shown here, and we're sort of allocating control between driver and controller, that's about it. I'll just conclude, just brief conclusion. We've designed a constraint planning mechanism that, as far as we can tell, is novel. We designed a mechanism for allocating control between human and machine to ensure that the human's inputs are honored where possible and overridden where necessary, and only as much as necessary to avoid collisions. And we think that this is something of interest both to us and to some of our sponsors, whom actually I would like to thank. Funding for this is coming from the USARO, also from DARPA. I want to thank also our collaborators at Quantum Signal LLC for their assistance with the experiments. And with that, I'll take just a couple of minutes of questions, and then we'll move on to the second speaker. And here's where it gets a little bit awkward. I'm actually chairing this session, so I'll stand here. So there's no chair. As chair, I guess I'll open it up to questions. Yeah, I saw a hand here and then here. Just go ahead.
I had a question regarding the homotony by which you are generating the optimal trajectory. The figure that you showed had in a lot of obstacle or in similar situations, but suppose there is a wide road and there is an obstacle ahead.
Sorry, suppose there is a what?
There is a wide road and there is a small obstacle ahead.
Okay.
Your optimal trajectory would try to place the vehicle right in between the obstacle and the other boundary, which is clearly a suboptimal path.
So so tell me the scenario again. We've got a wide road, we've got a single obstacle far away, and you're saying that the controller
won't your optimal trajectory be the line joining the current position of the vehicle to the lateral central line between the obstacle and the other end of the boundary? That means it will try to take the vehicle extremely far from the obstacle.
So you're describing, so number one, we're using a finite time horizon. So we're only planning over 2 to 3 seconds. So number one, if it's extremely far away, we're not even considering it yet. Number two, if indeed we've got a very narrow sort of opening on one side, I'll let you read the paper for more details, but these capture sets are considering sort of the size of the capture set. So for example, if we have a very narrow opening and a very wide opening, the constraint planner is planning constraints preferentially to bound the wide opening as opposed to the narrow restrictive one.
And I had a second question. Suppose an obstacle suddenly comes in front of the vehicle. would it be possible that your algorithm tries to push the algorithm towards the left and the human driver is pushing towards the right? So there's a contradiction between the human and the algorithm.
Yeah, and I haven't even talked about that, we're also considering the current state of the vehicle and the steering rate constraints, right? So if it's not possible, for example, for the vehicle to turn left around the obstacle, given its the current driver input, which presumably the vehicle is following if we haven't intervened yet, and the steering rate constraint, we won't design constraints that bound an infeasible area, right? It's considering what the vehicle can currently do.
My question is that suppose suddenly an obstacle comes in.
Yeah. Okay. So the suddenly restriction, in as much as we can sense and predict it, and that's where we get into some of the sort of prediction for environmental obstacles, and we won't get into any of that. In as much as we can sense and predict the motion of that obstacle, we can determine the dynamic feasibility, or at least the probability of dynamic feasibility of passing left or right, and we'll weight the constraint plan towards the more dynamically feasible one.
But my question is that in such a scenario, your algorithm is currently having a priority over the human driver. The vehicle will go as per your algorithm, and your algorithm wants it to go to left, and the human wants it to go to right, and the vehicle will go to left.
If a collision is imminent, yes. If a collision is imminent, the assumption is that the dynamic feasibility of going left or right is better calculated in a high-threat scenario, which I think is borne out actually in human factors research, showing that humans tend to perform poorly when surprised by sort of a lot of information. We do bias towards what the automation is decided.
And is the human in this algorithm more than a tool, as per your original motivation, because he's effectively not doing anything?
The human is actually biasing. We should actually talk offline. This is actually taking time from some of the other questioners. Let's talk offline, but the human is biasing the vehicle state, especially before a collision is imminent. Once a collision is imminent, whatever state the humans put the vehicle in is the one that the controller is going to try to get it out of if it needs to. And we've literally got 30 seconds left for questions. Does anybody have a quick question? Yeah.
From the figures and the pictures that you showed, it seems that you're looking into the global coordinate system. I would like to hear a bit about that, what coordinate system you're considering, and also about the convexity issues of the optimization problem. Thanks.
Yeah, thank you. So we're using linear model predictive control. There's actually a paper in this conference somewhere where they've used nonlinear, but we're using a combination of the two. We've actually got a pretty poor IMU right now on the vehicle, so we have to use the local frame for obstacle avoidance. So that's what we're using for the LiDAR. You'll notice, that's exactly why some of the shadows of my bounding boxes from obstacles are so transitory, is because our IMU is so poor. So global is only done in the sense that we're using global localization to determine the edges of sort of the traversable environment, right? And regarding your second point with constraints, they do need to be convex in lateral vehicle position in order for the model predictive controller to solve them. And which is exactly why we have to plan a set of constraints, a specific homotopy. And once we have that, we can make them convex, no problem. So we plan the constraints before we run the MPC controller. And the model predictive controller solution satisfies that set of constraints that we've planned, which are always convex. If we've planned it as convex. I mean, but if you have a single homotopy, you can design convex constraints, no problem. Okay. So while Professor Laufenberger is getting set up, I'll just introduce him. He's an associate professor in MIPS and MIAM. I'll let him define those to you. His research group is focused on modeling, identification, and control in automotive and aeronautical domains. His personal research topics include data fusion for assistance systems and for assistance systems design.
Thank you for this nice introduction. Welcome to my presentation. So there will be some close connection with the previous presentation, as you will see. So the title of this presentation is Reference Generation, Constrained Reference Generation, and Control Strategy for Automated Vehicle Guidance. So it's a work performed by Rashid Atia, who is PhD student in the lab, and Jeremy Daniel for the active researcher, I would say, on this work, and supervised by myself, Rodolfo Orjuela, and Michel Bassi. So the outline of my presentation will be as follows. I will just briefly introduce the topic, which will be developed here, and then I will focus on the two main points from today, which is the constraint path generation. Sorry. Yeah, thanks. Then I will go on to the two main parts of the presentation, which are constraint trajectory generation and the use of this reference generation for longitudinal and lateral control of car-like vehicles. Then I will show some simulation results before a conclusion of my topic. So currently, car manufacturer and also researcher have to deal with three main issues. The first one is that there is a constantly growing number of personal vehicles on the roads, and in the same time, we would all like to increase the safety during driving situations. And also at the same time, the third issue, which is growing currently, is to try to reduce greenhouse gases and also fuel consumption of our cars. So keeping the balance between these three aspects will be quite challenging for the next years. So if we look at the solutions based on driver assistance systems, there are currently on the market a lot of available systems, ABS, ESP, and so on, but none of them, or roughly none of them, are integrating the ecological aspects of gas emissions or consumptions. So one emerging field of research is now to develop ecologically friendly, so what we call eco-friendly driver assistance systems. This morning we had a presentation from Chris Hermson, who mentioned the fact that smooth driving can lead to very effective fuel reduction consumption, more or less to 20%. This is based on recent studies from 2010. What is smooth driving? Smooth driving means that we have to use smooth accelerations to anticipate traffic congestions, for instance, but also to drive perhaps under the legal speed limits. Unfortunately, there are more or less only few studies who are dealing with this approach. I saw last year in the conference, in the IV conference, only one paper dealing with fuel reduction in ADAS systems. So the final goal of our work would be to develop a driving assistance system which integrates safety and also ecological aspects. But here the main topic will concern the first step of this development, which is the development of a coupled control strategy based on longitudinal and lateral control of the car. So our approach is based on the use of a perception model, which has been presented last year in the conference. This is a fusion between a navigation system based on digital map database and a vision system who detects traffic signs and especially speed limit signs. Based on this information on the driving situations, we are defining a reference trajectory and also a reference speed profile for the longitudinal and lateral controller. And finally, the control aspect will be done using a nonlinear model predictive controller, which has been introduced by Sterling just before. So let's have a look on the vehicle guidance principle that we have adopted. So if we consider the vehicle here with the steering actuators and the propulsion actuators, so the engine, the first idea is to perceive the environment of the vehicle using a speed limit assistance system. So this, I will not go into the detail of the speed limit assistance system. You will be able to find some references in the paper about that previously developed system. The main idea is to be able to detect and to inform the driver about the limit, the speed limit he should not exceed during his driving task. So once we've located the vehicle on the map, we are able to compute two references, so one trajectory references and one speed profile references, which are then used by the controllers, namely the lateral controller, which is based on MPC solution. So we'll go first into the detail of the reference generation module and then into the control module, which is the core of this presentation. So if we consider that the vehicle must go from a starting point to a given destination, and that obviously this track must be on the road, so included in the boundaries of the road, we can, by considering the vehicle and the width of the vehicle and the width of the road, define what we call a validity area in which the trajectory can be constrained. This means that during this particular pass, the vehicle, the center of gravity of the vehicle, should not go out of this constrained boundaries. We can also add in top of that some other geometrical constraints. For instance, the curvature continuity constraints, which will be important for the steering. And also some constraints related to the geometry of the car, so the minimum turn radius. And we can also integrate in this optimization problem some kinematic and dynamic constraints in order to avoid, for instance, excessive lateral accelerations. So the solution that we've proposed is based on the optimization of this trajectory based on parametric cubic splines. So between the two reference points given by the navigation system, we are computing this reference pass using an optimization criteria which is based on the energy, the strain energy of the trajectory. This criteria allows us to minimize the curvature variation over the strain of the pass. So, what is the idea about minimization of the strain energy? The idea is that if we have smooth trajectories, so without high variation of the curvature, we should probably implicitly meet some eco-friendly concepts. So the smoothness of the curvature will allow us to have a smooth trajectory, as mentioned this morning by Chris, and then to be able probably to reduce the car consumption. Let's talk now about the speed profile which will be associated to this reference trajectory. So first, one speed information will be provided by the perception level, so the speed limit assistant, which uses the detection from the traffic signs with the information provided by the navigation system. After that, we are also taking into account the road topology because the speed profile should match with the generated trajectory. So based on the reference trajectory and its curvature, we are computing a speed limit profile using a very simple model which is defined in the literature, which only limits the lateral acceleration during that pass. Finally, we will also we have also integrated some comfort aspects in order to limit the variation or the decelerations and accelerations given by the driver. So these are comfort aspects, but smooth deceleration and accelerations are also related to fuel consumptions. So the idea is here to use a triangular shape for the acceleration or deceleration phase and to recompute in real time the speed profile in order to adapt it to this triangular deceleration or acceleration shape. And the last step is a verification of the speed limit of the speed profile which has been generated in order to ensure the stability, the lateral stability of the vehicle. So now that we have a better idea about the reference that we are using for the controller, let's see how we've implemented these controllers. So the nonlinear model predictive controller is based on the single track model. So it's a very famous model. We are using a nonlinear bicycle models for the controller synthesis, which allows to consider coupled dynamics and kinematic constraints. It is used on the assumption of variable longitudinal speed. Our speed profile will not be constant during the whole pass, as I will show it in the simulation. And finally, we've integrated in this model a nonlinear Burkhardt tire model to estimate the tire forces on this model. So I will probably briefly, I will skip this slide because it had been presented previously by Sterling. So the idea is just to recall the assumption of model predictive control. If you have here a reference trajectory, the model allows you to define the predicted output of the system. And based on this predicted output, by minimization of a cost criteria, you can define the control sequence for your system. And basically you can add some constraints also on the control inputs and on the control input variations to limit this, their values. So the scheme that we have adopted here in this work is presented here. We have our lateral the guidance system based on the NLMPC and a classical cruise controller to maintain the reference speed, and the coupling is ensured by the variable speed, which is considered by both systems. So the NLMPC ensures the tracking for time varying speeds, and the cruise controller allows to maintain the vehicle speed. And this variable vehicle speed has some effects on the lateral dynamics of the car. So now let's go to the results that we have obtained with this solution. So first I will show you the implementation of that on our test car. So one part, this part has been completely implemented on the test car and validated in real-time conditions. So we are using the navigation system provided by Navtec, whose name is ALSRP, in order to locate the vehicle, to generate in real time the trajectory using the spline model. And the data from this navigation system are fused using RTMap software from Intempora with the camera detection with the camera detection of the traffic signs. Once we get this information and the reference trajectory, we are using these references to generate the speed profile and then to do the simulation in MATLAB Simulink about the control of the car. This part is validated offline, so in simulation. The test that I will show you represents one sequence that we've recorded on a typical highway close to the university in Mulhouse, in the east of France. So we'll go through a highway exit ramp before a variable radius curve, and then we will reach another highway and perform here a lane change before getting into the next highway section. So as you may notice, we will here have important speed, 110, and we will then have to sequentially brake until 50 kilometers and maintain 50 kilometers, which is the legal speed limit for the whole bend before reaching here the straight line. So this first, just stop it. This first video shows the results of the perception and of the SLA, so the speed limit assistance system. You will see here the trajectory that we will, so the path that we will follow. On the right side, you will have the information provided by the navigation systems after an internal fusion of some information from the navigation. On the left side, the results of the speed limit traffic sign detection, and in the middle, the results of the fusion. So this has been recorded, and these tests have been done in real time, and at the same time, we've computed the reference trajectory, which will be used for the control. So here we will follow this car, we'll take this exit bend, and you'll see that we have detected a speed sign limiting the speed to 90 kilometers per hour, and then we will take progressively the right turn. So a new traffic sign has been detected and the system already changed. And here now the speed is limited to 50 kilometers until the end of the bend. And here we are in real-time conditions, so we are really driving in with 50 kilometers. Even if you can see that probably we could drive faster in this situation, which is not legal. So and just after the bend, in order to enter the next highway situation, we will have to do a lane change, but which will not be presented here. So from here, we will have to do a lane change to reach the next section. So now let's see the trajectory which has been generated and the speed profile adaptation which is performed. So I will just stop the video in order to give you some explanations. Okay. So here on the right top plot, you can see the reference trajectory based on splines, which has been generated for the whole pass. This is just a section of that trajectory, which is presented here in red. I don't know if you can see it very well. So it's just a section trajectory and with the corresponding speed profile. So you can see that based on the detected information or detected speed limit by the SLA, we have to change the speeds from 110 to 90 to 70 and to 50. And by integrating the different criteria we've mentioned, we will then smooth this speed profile in order to be used by the controller. So using the triangular shape of the deceleration, you can see that the speed profile is smoothed. And if we go through the whole simulation, you will see that each time that the system has to decelerate or reaccelerate, we completely smoothed that speed profile. And that's in the whole turn, in the whole band, because now we are completely in the band, the speed is lower than the legal speed limit. So this should probably have some positive effect on the consumptions. So as we are reaching the end of the band, you can see here the lane change maneuver which has to be performed and followed by the NLMPC, by the lateral controller. So that's it. So now let's see the results of the lateral controller. So for these simulations, the vehicle has been simulated by a 4 wheels 2D nonlinear model. It's not working. Okay. We've considered that the road is flat and that we are on a dry surface, so with a maximal grip. And finally, that the control inputs are the steering wheel and the wheel torque. And here you have the results of the path tracking based on the NLMPC. So you can see that the system effectively tracks the reference path, and that the speed has also been tracked quite correctly. There are some basic, I would say, overestimation of the heading angle. This section here corresponds to the lane change. This is probably the limit of the model predictive controller we've implemented here, but in the whole case, the reference trajectory is well followed, and also the speed profile. So coming to the conclusions, I've presented you a coupled longitudinal and lateral controller for automated guided vehicles based on the data fusion between two relevant and complementary systems, which allow to have access to very important geometric information. I've also showed you how we've developed a constrained trajectory generator for the lateral controller in order to obtain smooth trajectories. And finally, how we are computing a speed profile based on several criteria related to the driving comfort, to the lateral dynamics, or also to the longitudinal dynamics. Finally, we saw during the simulation that this coupled control provides safe and effective tracking in simulation. And the outlooks of this presentation, of this work, will first be focused on the implementation of the lateral controller on the car, and probably that we will have some other results during test tracks. And finally, to the real integration of explicit ecological-based criteria. I showed in the presentation the fact that until now we are only considering implicit criteria related to these ecological aspects. Thank you very much for your attention, and I'm ready to answer your questions.
Did you have any constraint on the acceleration?
Yeah. So with the triangular shape of the acceleration profile, we can fix the maximum that we want to reach, or the minimum we want to reach for decelerations. So that can be fixed.
But from the graphs, it looked like they accelerate quite slowly. I guess most drivers would like to accelerate faster.
Here in the simulation, I think that we used an acceleration, a deceleration from 3 meter per 3 meter second square, and the acceleration is a little bit lower, which corresponds to traditional values that can be found in the literature related on driving comforts.
Thank you.
Right here.
Are you considering the integrated longitudinal and lateral support, or I mean, I'm thinking about the friction circle. How do you deal with that if you have the integrated longitudinal and lateral input?
You mean so
I mean, for instance, in the suddenly changing corridor, I would say, in the MPC approach, if you brake hard, you can't steer at the same time. At least you lose some friction for doing the lateral intervention.
Right.
How do you also considering that?
This is not directly, so explicitly considered in the NLMPC. So we've bounded the steering input and also the steering variations. So, but we have not explicitly bounded the fact that you cannot decelerate or steer the wheel if you are decelerating or accelerating. But since the reference path that we have generated is based on the smoothness of the trajectory, we avoid high curvature trajectories. But this does not mean that the tracking systems or that the controller will be able every time to follow that path. If he goes outside, we can have some instability of the system, but until now it has not been the case.
And my second question, you are considering the third order polynomial for the trajectory generation, which means constant jerk.
Mm-hmm.
Do you think that it's appropriate? Because usually the drivers try to drive in the continuous jerk. How do you think about that?
So with this mathematical model, there is no assumption on the jerk. I think the only thing is the assumption on the curvature. So it's continuous in curvature.
Yes, but the trajectory will be constant jerk, which means that if you want to follow that, then you will not have the driver behavior type of intervention, I would say.
Yeah. But yeah, this can be effectively one problem. But as I showed in the presentation, if you want to consider ecological aspects or fuel reduction, you will probably go outside of the average driver behavior. One of the things is that normally you should drive below the speed limit in order to reduce fuel consumptions. So in France, currently there are a lot of, let's say, coaches who are learning people how to drive ecologically. And they tell them to drive under the speed limit and to drive with limited acceleration and deceleration. So probably that this part of the jerk limitation, of the constant jerk, will also be avoided based on these concepts.
Thank you.
Okay. Let's thank our speaker.